Hi, this is Professor Fernandez, and we're talking here about video 2 in lesson 10. Topic is the power rule, and I'll show you what that is in through three examples here from Calculus Simplified. Okay, so this is the topic where, as we've been talking about in the this video series, differentiability can take a while. If you use the limit definition of the derivative, it's cumbersome to calculate the limit, it takes a long time. In video 10.1, which is basically all the scribbling that you see here, we talked about the derivative rules, the most basic ones, the sum, difference, and constant multiple rules. We'll use that in these three examples, so you might want to check out that video. And what else will we use? Well, we're going to use the power rule. So let me just review real quickly what the power rule is. Here it is down here. This is theorem 3.4 from Calculus Simplified. So suppose n is a real number. Then the derivative, this is what the symbol indicates, of the function x to the n is nx to the n minus 1. Some quick examples. The derivative of x cubed is you take the, let's put a different color here, make it easier. You take the exponent, you bring it down, so bring down to 3, and then you write x, okay? And then you subtract 1 from the exponent, 3 minus 1. So this would be 3x squared, 3x squared, the derivative of x cubed. So I'm trying very hard here to put everything in the same color to help you see the pattern. So, short of an animation where I can somehow take this 3 and like bring it down, like, the 3 comes down this way, right? The idea is hopefully clear that whatever number is here becomes the multiple of the new power function. And whatever number is here, you subtract 1, and that becomes the exponent of the new power function. That's the power rule. That's what it says down here. And here, the original exponent can be any real number. So the derivative of, x to the pi, right? Pi is the irrational number. That's about 3.14. Would be, bring down the pi, x to the pi minus 1. Kind of crazy to think about, but it is what it is. Something else, the derivative of x to the square root of 7, right? Would be square root of 7, x to the square root of 7 minus 1. Okay, so really applying the power rule is perhaps the simplest thing that you could possibly do in differentiation. Almost everything else is more complicated. So finally, we get to a point in derivatives where the concepts are fairly mechanical and fairly simple and straightforward to apply. That doesn't mean that it's not going to be without its little hurdles, if you will. Some functions, and you'll see this is why I want to do 3 examples, some functions are going to be presented in a way that mask the applicability of the power rule. I'm thinking specifically about here and also here, but we'll get there, right? So let's talk about this first example. Okay, differentiate x cubed minus 3x. I'm going to zoom in here. So I'm looking for f prime of x. It's x cubed minus 3x. This is where I mentioned before that you might want to check out video 10.1 in this series, because that talks about the sum, difference, and constant multiple rules. I'm going to use that here, right? So x cubed 3x, I'm going to say this is the derivative of x cubed minus the derivative of 3x. You might remember in video 10.1 I made a big fuss about using theorems. If you're going to use them, you should verify the hypotheses. Right? X cubed is a cubic function, looks like that. It is nice and differentiable everywhere. We can draw slopes of tangent lines everywhere. Every polynomial, in fact, is differentiable everywhere. So 3x is a linear function, looks kind of like that. Same deal. I can draw tangent lines everywhere, so it's differentiable everywhere. It is also a linear function, a polynomial. So that's kind of my just quick check to make sure I can use the theorem that I'm using. I can separate the difference of the functions, the derivative of the difference, into the difference of the derivatives. I won't always do that check, even though I'm going to encourage you to at least give it some thought. But often, if we just say differentiate, whoever your instructor is, unless we say verify, we insert here, verify that one can differentiate, and then differentiate, right? If we don't make it clear, chances are that's not the skill or topic or concept that we're testing you on. We probably want to test you on something else to assess how well you have mastered something. And in this case, it's the power rule. Anyway, so having talked about that, let's continue our calculation here. So now we're to the point where we have, hey, two power functions, right? X cubed is a power function. What is its derivative? Well, we kind of just did that example. We would bring down the 3, subtract 1, oops, 3 minus 1. So we get 3x squared. So the derivative of x cubed is 3x squared. Awesome. So I'm going to write that over here. That's my derivative, 3x squared. 3x, so this is what I said about a minute ago, that applying the power rule is fairly straightforward and simple, but it's really the complications come in the presentation of the functions. 3x, how do you apply the power rule there? Well, this is 3x to the first, right? So the 1 is hidden, but it's there. So to apply the power rule to differentiate it, okay, I am going to bring down, first of all, let me apply the constant multiple rule. Write this as 3 times x to the first, and I'm differentiating that. And now I'm going to bring down, applying the power rule here, I'm going to bring down the 1, and then subtract 1 from the exponent, which happens to also be 1. So it's 3 times 1x to the 0. In other words, 3 times 1, which is 3. So that is my derivative for 3x. And that is, again, a way, basically the way to differentiate 3x or 7x or any number times x, right? So the rule that we've just realized is that any number times x, when differentiated, gives that number. Okay, so this is a nice little derivative rule you might want to remember. But again, if you don't want to remember that specific rule, that's the point of doing this process, right? Understanding the power rule in all its manifestations so that you can apply it correctly. So f prime of x, 3x squared minus 3 for this function up here. Great, let's move on to the next example. So g of x is 10x to the 9th minus 3 root x. So if I want to find the derivative, then I am going to be doing something somewhat similar in the sense that it is a difference of two functions. So the difference of the two derivatives. Each one of these is a multiple of another function. So I'm going to pull out that multiple using the constant multiple rule. Great. The first one now I can do fairly quickly. So x to the 9th, bring down the 9, subtract 1, 9x to the 8th. That is the derivative. I still got to multiply by 10. And then this one, back to the same thing I've been saying, presentation of the function. How do I differentiate root x? Well, I have to first express this as a power function. So again, a lot of this goes back to being able to accurately classify families of functions, or just functions in general. And we talked about that in the first few videos in this series. So writing it as x to the 1/2, now I can see it as a power function. The n from x to the n in the power rule is 1/2. So the derivative is going to be bring down that number, x to the subtract 1 from that number. So the derivative here is 1/2 x to the minus 1/2. How did I get that? Well, 1/2 minus 1, 1/2 minus 2 over 2, 1 minus 2 over 2, negative 1 over 2. So that gets me back here. Okay, and then last thing, remove some clutter here. 1/2 to the x minus 1/2 times x to the negative 1/2. Remember, negative exponents mean that the x to the negative 1/2 becomes reciprocated. So it's 1, it becomes 1 over x to the 1/2. And then if you wanted to, you could go back and remove the fractional exponent and put the radical back in, 1 over 2 squared of x. Okay, so if we zoom out, the derivative of square root of x is 1 over 2 square root of x, or 1 over 2 x to the 1/2, same thing. So I'm going to plop that in here, 1 over 2 square root of x. And then I could just simplify a little bit. I have a 9 times 10 over here on the left. That's 90 x to the 8th. X to the 8th. I have a 3 times 1 over 2 root x. That's 3 halves root x. So this is my derivative. Okay, so let's see what is up next over here. So we have differentiate h of x equals this function. So let me take a quick second to double check. Yes, I'm just making sure I haven't made any small mistakes. Mathematicians are known for doing that when teaching calculus. So differentiate this function. H prime of x equals 2 over x cubed plus 5x to the 1.2. Take the derivative there. Okay, once again, we can use some of those basic rules that we talked about. This is the sum of these two functions, so I'm going to split up the derivative into the sum of these derivatives. Then constant multiples, I can pull out the 2, 1 over x cubed. I can pull out the 5, x to the 1.2. Okay, let's do this one first because it's already in power function form. So I'm going to bring down the 1.2 x and then subtract 1 from 1.2. So that's 1.2 x to the 0.2. Great, so that's done. How about this one? Same mantra as before. It's all in the presentation, right? So 1 over x cubed, how can I view that as a power function? Well, I can write it as x to the negative 3, right? Again, negative exponents reciprocate. So if I differentiate 1 over x cubed, it's like differentiating x to the minus 3. And now I see it as a power function. So I bring down the power, negative 3, x to the negative 3 minus 1, negative 3, x to the negative 4. Great. So I'm going to take that and put it in over here. 2 times negative 3, x to the negative 4. Okay. So there's a lot going on. So I'm just going to take this part first, multiply the 2 and negative 3. I get negative 6, x to the negative 4. And then over here I have 5 times 1.2. So that is 5 times 1.2. 5 times 1 plus 0.2. Distribute the 5. 5 plus 5 times 0.2. What is 0.2? 0.2 is 2/10, which is 1/5, which tells us that the 5s go away and I get 1, so I get 6. I didn't need to do all that, but I wanted to do all that to remind you a little bit about some of the properties that come in handy when you are trying to simplify. You work with decimals, convert decimals to fractions and things like that. Always comes in handy to know those things when you're calculating derivatives and just working with all these different numbers. Okay, so this is a slightly more clean version of this, and then just to clean it up, you could stop here. This is the correct answer, but notice that they all have a 6 in them, so both terms. So I can factor out a 6, be left with x to the 0.2 minus 1 over x to the 4th. So again, here I use the fact that x to the 4th is 1 over, sorry, over here is 1 over x to the 4th. Great, so let me zoom out here and give you a couple of tips. As I've been sounding like a broken record now, saying throughout this video, it's all in the presentation of the function in terms of using the power rule. This is the first one that we met that was perhaps a tiny hurdle. How do you view x as a power function? Well, it's x to the 1st. That helped us over here to then differentiate 3x to 3. 3 square root of x, how do you view square root of x as a power function? That's over here, it's x to the 1/2. And we differentiated that to 1 over 2 square root of x. 2 over x cubed, right? How do you view something over x to the whatever as a power function? Well, that turns out to be a negative exponent, right? So 1 over x cubed down here is x to the minus 3, and that helped us with the power function representation, and then the power rule applies. Okay, and then very last thing I'll say, remember, we're still in the background. We will always pretty much from now on be using those foundational rules, the sum, difference, and constant multiple rules. So if you want to see more of that, again, check out video 10.1. Thanks for watching.